Hello everyone, this is Dr. Lennon, and today we're going to be talking about parametric equations. So the basic idea of parametric equations is that we want a way to describe graphs in another way using a third variable, time. Idea, introduce a new time variable t in order to describe explicitly in terms of t how x and y behave. So essentially what you're going to have, if you had some equation y equals f of x, now what we want to do is we want to explain it in terms of two functions of each variable, x of t and y of t. So basically, rather than y equals f of x, we use a pair of equations x of t and y of t to describe our ordered pairs. Okay, so rather than just having an x comma y ordered pair, you have an x of t and y of t ordered pair. And in this sense, your equation is not going to be unique. Not only it'll describe the same curve, but you can actually talk about different speeds at which you go around a curve. So let's look at a simple example. And a lot of times these will describe things that aren't even necessarily functions but relations. So example, consider x squared plus y squared equals 1. What we want to do is write a set of parametric equations to describe the same curve. And then a follow-up question, are those equations, parametric equations, unique? So, not such a hard question because we know the object that we're graphing is just the unit circle, right? X squared plus y squared equals 1 is the unit circle. So the graph is just the circle centered at 0, 0 with a radius of 1. Well, we know from trigonometry that any point on here can be described. You can describe the coordinates using cosine and sine. So that is exactly what our parametric equations are. So, right, we can use sine of t and cosine of t to describe this parametric relationship. So we could say x equals cosine of t and y equals sine of t are one such set of equations. Right. How long is it going to take that set of parametric equations to describe the entire circle once? Well, from t equals 0 to t equals 2 pi, we traverse the curve once. So the follow-up question, is that collection of parametric equations unique? The answer is no. They are not unique. So, for example, x equals the cosine of 2t, and y equals the sine of 2t. We'll draw the same graph. And one thing we can note further is it's actually going to draw the graph twice as fast, because now between t equals 0 and t equals pi, you'll traverse the curve once. So note that this set of equations draws the above curve twice as fast. If we're thinking about t as being in terms of speed, it would take 2 pi seconds to draw the curve with the first set of parametric equations, but now it will only take pi seconds. Drawing it once. From t equals 0 to t equals pi. So that's the first example, and that's the basic idea. Sometimes it's more difficult to find a set of parametric equations. Sometimes it's easier. Sometimes it's based on something you know, like from trigonometry here. Sometimes it requires a little bit of algebra. So we'll jump in with our next example here in one moment. Okay, so if we're looking for a way to, so this example, we want to confirm that the parametric equations x of t equals 2t and y of t equals 1/2 t squared minus 4, in fact, are the graph of a parabola. So usually the easiest way to do this, it's not always easy to do, it depends on how difficult it is to solve for t, is solve for t in one of the equations and plug it into the other one. So here, basically, we know x is equal to 2t, so x over 2 is equal to t, and then we basically plug this into y of t. And rather than writing y of t like with differential equations, I'm just going to write y. Y will equal 1/2 x over 2 quantity squared minus 4. And we see we end up with something of the form y equals x squared over 8 minus 4, which is clearly a parabola. It's essentially x squared flattened and shifted down 4 units. So a lot of times that's a little bit more straightforward than actually finding a set of parametric equations, but also useful to remember. Solve for t in one of the variables. Again, sometimes it'd be x, sometimes it'd be y, but usually for us, we're accustomed to x being the input variable, so I would always look there first. Okay, another class of equations that comes up all the time in practice, right? Motivation for Calculus 1 are the linear functions. So here I just had find some parameterizations for y equals 3x plus 4. So it might be helpful to just think of maybe like some x, y table of values where we plug in a few. And then from there we can quickly realize what they're going to look like. So let's say we plug in -2, -1, 0, 1, and 2. Well, if you plug in -2, you're going to end up with -2 for y. And then you're just adding 4 each time. So we're going to get, adding 3 because that's the slope. Not 4, that's the y-intercept. So we get 1, 4, 7, and 10. And then what we want to do here is, to find parametric equations, you just want to think about what you want to choose t to be. and confirm that that it gives the corresponding x and y values. And there's lots of ways to do this. One very simple way would be, say we just chose x to be t. So if we let x be t, then simply y would be 3t plus 4. It would be the exact same thing. And notice, basically, we'd end up with t values just matching your x values, and then the equation remains the same for finding y. Another one, what if we had, say, x were equal to t minus 2? Let's say we just made a linear shift to x. What would happen to y? Well, again, x would just be replacing the t minus 2, so it would look like the same above equation, y equals 3, but then instead of t, we'd have t minus 2 plus a 4. What's another example of like a linear change? Say we wanted x to maybe move more slowly. So let's say we do t divided by 2. So then what would happen to y? Well, again, we'd just be replacing the t in equation 1 with t over 2. So we'd end up with y equals 3t over 2 plus 4. So those are a few examples of parameterizations for y equals 3x plus 4. In general, we can do this for all parametric equations of lines. So in general, so that way if you're looking at a parameterization, you can recognize a line. The parametric equations of a line have the form x equals some x0 plus at and y equals some y0 plus bt. So in general, what do these things represent? So what's going on is, where x0, y0 is a point on the line, and the slope is m equals b over a. So you can kind of look at the equations above and notice that we satisfy these properties. So this is something useful to remember anytime you have a set of equations of lines. One thing we care about is how does this relate to some of the concepts we've learned in calculus? Why do we care about parametric curves? You've probably seen them in pre-calculus before, so basically let's look at theorem, and this is just how we take the derivative of a set of parameterized curves. So so put that in parentheses, derivative for parametric curves. It's pretty easy and exactly what you would expect. So let x equal some f of t and y be some g of t. Suppose they are differentiable for t in the interval a to b. Then the slope of the tangent line at t is given by So dy dx basically just means we're actually going to take the derivatives of the two parameterized curves. So dy dx basically would say to do dy dt over dx dt. And those are just the derivatives of the parametric equations with respect to t themselves. So this would be f prime of t. Oh no, y is g, sorry. So g prime of t over f prime of t. Provided f prime of t is not equal to 0. So, pretty straightforward, exactly what you'd expect. Let's go ahead and do one such example. So we'll do this, then we'll do one with arc lengths. And then that will be it for this first section. So, what do we want to do? Let's find the slope of the tangent line to x of t is equal to t, and y of t equals 2 square root of t at t equals 4. Okay, so how do we do this? Well, first we want to find the derivative formula and then go ahead and plug in the t value we care about. So dy dx here is given by the derivative of y of t, which we have to take the derivative of the square root of t, which is going to be 1/2 t to the negative 1/2, and the 1/2 will cancel with the 2 in front. So y prime of t is just t to the negative 1/2, and the derivative of x is just going to be 1. So we have essentially 1 over the square root of t, and at t equals 4, this is just going to be 1 over the square root of 4, which is 1/2. So it's as easy as that. Okay, so now let's talk about the arc length formula, and remember how we found the arc length formula in general. So arc length of parametric equations. Okay, so let's see where this comes from. So let's recall the the old formula, let's say, said arc length was, let's just say it's equal to, if we have some function f of x, let's say, it's going to be the square root of 1 plus f prime of x. Well, let's just use dy dx, in fact. That'll make things a little bit cleaner. 1 plus dy dx squared times dx. So then let's use the convention above. So suppose the function has the parameterization like we were using above. Let's say x is equal to f of t and y is equal to g of t, then we can essentially plug in everything we want. So our arc length now, so the equation above will just become the same integral. Now maybe a and b are t values, but just take that with a grain of salt. Those can always be adjusted or reformulated. But now what we have is 1 plus g prime of t over f prime of t, quantity squared, and that's what's inside the square root, and then outside the square root we're now multiplying by dx is going to be the same thing as f prime of t. So usually, and now we're doing this all with respect to t, so we'll write a dt on the outside. That f prime of t can be brought inside, right? Because f prime of t is the same thing as the square root of f prime of t squared. So this can be rewritten as the integral from a to b of the square root of 1 plus g prime of t over f prime of t squared times f prime of t quantity squared, that's what's underneath the square root, times dt, and then that becomes simplified a bit. So when you distribute the f prime of t squared, now what we have is we just have the integral from a to b of the square root of f prime of t squared plus g prime of t quantity squared times dt. So remember, arc lengths were pretty complicated when we had regular equations, but a lot of times if you have a set of parametric equations, the arc length can be much simplified. So let's go ahead and just do a quick example demonstrating that this works for, say, a circle where we know the arc length already, so we can quickly check if our answer works and that this formula is correct. So let's find the area of the circle of radius lowercase a using f of t equals a cosine of t and g of t equals a sine of t from t equals 0 to t equals 2 pi. So those are going to be our integration limits for this example, 0 to 2 pi. So our arc length is the integral from 0 to 2 pi of the square roots. The derivative of a cosine t is going to be negative a sine of t, but when you square it, you'll get a squared sine squared t. The negative, when you square it, goes away. And for the second term, you'll get a squared cosine squared of t. Then what you can do is you can factor out the a squared. So the square root of a squared is just, we can, square root of a squared is a, which we can bring out front. So we get a from 0 to 2 pi. And then this is the square root of sine squared t plus cosine squared t, where we can bring in the Pythagorean identity, and we know that the sum of the squares of those two terms is equal to 1. So we just get a times the integral from 0 to 2 pi of 1 dt, and integrating gives 2 pi times a. So that's exactly the circumference formula for a circle, right? It's going to be 2 times pi times the radius of that circle. So that's exactly the circumference formula as expected. Okay, so that's it for introducing parametric equations and their applications to the derivative and the arc length formula.